Scientists say the ice sheet around Greenland is melting at an unprecedented rate.
Nearly half of Greenland's ice sheet began melting this week.
Greenland's melting ice sheet is contributing to a rise in sea levels.
What if the ground beneath one of the most frozen places on Earth has been quietly hiding secrets for nearly 3 million years, and scientists just found the key to unlocking them? Beneath nearly 2 miles of ice in Greenland, scientists have uncovered something extraordinary, an ancient world frozen in time.
The situation became more urgent this summer when 11 billion tons of surface ice melted in just one day.
From preserved landscapes and fossilized ecosystems to massive hidden lakes, this discovery is a glimpse into Earth's past that was never meant to be seen. And now researchers say these findings could completely reshape how we understand climate, history, and even the future of our planet. Subscribe and hit the bell. This is just the beginning of what's hidden beneath Earth.
For years, scientists have been carefully measuring Greenland's glaciers and watching them collapse before their eyes.
Why Greenland is one of the most studied places on Earth. Greenland is enormous. Its ice sheet covers roughly 656,000 square miles, making it about the same size as Alaska. It holds the second largest body of ice on the entire planet, trailing only Antarctica. Scientists have been obsessed with it for decades, and for good reason. That ice sheet, if it fully melted, would raise global sea levels by about 23 feet. That would permanently flood cities, coastlines, and low-lying countries around the world. But here is the thing that makes Greenland so scientifically valuable. It is not just a warning sign for the future. It is also a record of the past. The layers of ice stacked up over millions of years contain trapped air, ancient dust, and frozen soil that tells the story of what Earth's climate has been doing for a very, very long time. Every drill core pulled out of Greenland is like opening a time capsule. What surprises most people is that even with all the attention and research, scientists freely admit there is still a lot they do not understand about what is happening beneath that ice. The base of the Greenland ice sheet, the place where ice meets the ground, has remained largely mysterious. Getting to it is not easy. The ice is up to 2 miles thick in some places, and what researchers have found when they finally reach the bottom has repeatedly shocked them. Scientists from institutions around the world, including Harvard University, NASA's Goddard Space Flight Center, the University of Bergen, and the University of Vermont, have all contributed major pieces to this puzzle in recent years. Together, their findings are building a portrait of Greenland that is far more complex, far more dynamic, and far more surprising than the frozen wasteland most people imagine.
Greenland's ice sheet is more than 3,000 meters thick in some places. If it melts entirely, global sea levels could rise by 7 meters.
The ice core that changed everything. In 1993, a team of scientists completed one of the most ambitious drilling projects in history. They pulled a single continuous core of ice out of the Greenland ice sheet at a location called Summit, Greenland. That core went down 10,019 feet, more than 3 kilometers into the ground. It took years of work, careful drilling, and meticulous preservation to get it out in one piece. Most scientists studying that core were focused on the ice itself. They were looking at the air bubbles trapped within it, measuring ancient concentrations of greenhouse gases, tracing the history of volcanic eruptions, and mapping out past temperature swings. That work produced extraordinary results on its own. But one geologist, Paul Bierman from the University of Vermont, was interested in something completely different. He wanted to look at the very bottom of the core, the dirty ice at the lowest 40 feet, where sediment and soil had gotten mixed in with the frozen water. When Bierman and his team finally analyzed those samples, the results floored them. They had expected to find very little of the chemical isotope called beryllium-10 in those samples. Beryllium-10 forms when cosmic rays hit Earth's surface, and since Greenland had supposedly been covered in thick ice for millions of years, there should not have been much of it. Instead, they found millions of these atoms in the samples. That was the moment when Biermann realized they had found something extraordinary. He later said they had expected to find a needle in a haystack, but instead found an elephant in a haystack. What the beryllium-10 levels told them was that the soil at the base of the ice had been sitting at the surface, fully exposed to sunlight and cosmic radiation, for somewhere between 200,000 and 1 million years before the ice covered it. This was an ancient tundra, preserved in a perfect frozen state, untouched for nearly 3 million years. Greenland had once been green.
Now, we don't know yet what exactly the weather impacts will be from melting ice sheets, but scientists are hoping that the answer lies in the cores of sediment they collected from the Greenland ice sheet.
A frozen world below 2 miles of ice. The idea that a living tundra landscape could survive intact for almost 3 million years beneath a moving, grinding ice sheet sounds almost impossible. Glaciers are typically described as nature's most powerful bulldozers. They grind down bedrock, scour valleys, strip everything off the land. That is what most textbooks say. But the Greenland ice sheet at its center, it turns out, does not work that way. The key is temperature. When the base of an ice sheet is frozen solid to the ground, the ice does not move across the surface. It does not grind or scrape. It simply stays put, locked onto the bedrock and soil below it, like a perfectly sealed lid on a jar. Scientists call this a cold-based glacier. The central region of Greenland sits in exactly these conditions. The ice there has been frozen to the bed, acting not as a bulldozer, but as what geologist Paul Biermann called a refrigerator that preserved this antique landscape. The ancient soil found at the base of the ice core contained measurable amounts of nitrogen and carbon left by plant material. Some of the organic matter suggested the pre-glacial landscape may have been a partially forested tundra, somewhat similar to the Arctic tundra that exists today in Alaska's Brooks Range. When researchers compared the chemical signatures from the Greenland soil with samples from that Alaskan tundra, the values were remarkably similar. Greenland really did look like that, millions of years ago. This discovery shifted the scientific understanding of how ice sheets behave. It showed that ice sheets are not always aggressive forces of erosion. In the right conditions, they can be extraordinary preservers of ancient landscapes. It also told scientists something important about the ice sheet's history. The center of Greenland has likely never fully melted, even during previous warm periods in Earth's past. That central region has held together through extraordinary amounts of warming and cooling over millions of years.
Greenland's ice sheet shed around 11 billion tons of surface ice in just one day in August. That's enough to fill around 4.4 million Olympic-sized swimming pools.
What that ancient soil tells us about climate history. The survival of a nearly 3 million-year-old tundra beneath the ice does more than satisfy geological curiosity. It provides a window into how Greenland's ice sheet has responded to past climates, and that history matters enormously when scientists try to predict what comes next. For decades, some climate models suggested that during warm interglacial periods in Earth's past, the entire Greenland ice sheet may have melted away completely. The discovery of preserved ancient soil under the center of the sheet provides evidence against that idea, at least for the central region. The tundra could not have survived intact if the ice above it had vanished and then reformed. The conclusion from the research was clear. The center of Greenland likely held on through those warm episodes. As co-author Tom Newman from NASA's Goddard Space Flight Center put it, "We don't know how much of the ice sheet remained, but these data suggest it did not completely melt." This is genuinely important for building accurate climate models. If you assume the ice sheet fully disappeared during warm interglacials and then compare that to what actually happened, your model is going to give you wrong predictions for the future. The Greenland soil data helps anchor those models to reality. giving scientists more confidence in how the ice sheet has actually behaved over geological time. However, researchers are also careful not to take this as reassurance. The current warming trajectory is heading into territory that has not been seen in millions of years. Paul Bierman put it directly: the ice sheet survived earlier warm periods, but if we stay on our current path, it will not survive. And once you clear a massive ice sheet off a continent, getting it back takes an enormous amount of time.
Icebergs broken off glaciers fill fjords.
Ice melting here in Greenland is affecting sea levels around the world.
The Hiawatha Crater. Deep in northwestern Greenland, beneath Hiawatha Glacier, there is something remarkable hiding under a kilometer of ice. A 31-kilometer-wide impact crater left by a meteorite or asteroid. The crater is wide enough to swallow Washington, D.C. It was hidden so thoroughly beneath the glacier that it took modern ice-penetrating radar technology to reveal it. The discovery was led by Kurt Kjær, a geologist at the Natural History Museum of Denmark. He had flown over the area by helicopter and noticed something unusual about the shape of Hiawatha Glacier. Instead of advancing in a straight wall toward the Arctic Ocean, it pushed forward in a conspicuous semicircle, as though spilling out of a round basin. Kjær suspected the glacier was sitting on top of a buried impact structure. To confirm the discovery, scientists flew aircraft equipped with next-generation ice-penetrating radar across the glacier's wings and body. The radar saw the contours of an enormous bowl-shaped depression beneath the ice, consistent with a meteorite impact. Kjær then led a ground team to the rivers draining the glacier, collecting rocks that had been swept out from beneath the ice. The mineral crystals he brought home clinched the case. The impact was real. Harvard University geochemist Stein Jacobsen, who studies impact craters, commented on the significance of the find. The Hiawatha crater is estimated to have formed during a period when humans were already present on Earth. Scientists believe the impact would have melted an enormous amount of ice and sent meltwater pouring into the North Atlantic Ocean, potentially disrupting ocean circulation and causing significant climate cooling at the time. The exact timing and full effects of this ancient impact are still being studied, and it continues to be one of the most intriguing buried features on the entire planet.
And right now, the Greenland ice sheet is melting, and it has been very resilient to climate change, but it is melting all over the surface.
The mystery of the swirling plumes inside the ice. For more than a decade, scientists studying the interior of the Greenland ice sheet kept seeing something they could not explain. Deep below the surface, there were enormous swirling column-like structures, almost like pillars rising up from the depths of the ice. Scientists called them plumes. They were real, consistently visible in the data, and nobody had a convincing explanation for why they were there. Ice is supposed to be solid. When you think of a glacier or an ice sheet, you picture something rigid and still, maybe moving slowly under its own weight, but not churning internally like a liquid. So the existence of these swirling plumes was genuinely puzzling. Researchers proposed various ideas over the years, but none of them fully fit. The plumes sat there as one of the unresolved mysteries of glaciology, baffling researchers well into the 2020s. Then in early 2026, a research team led by glaciologist Robert Law and Professor Andreas Born from the University of Bergen published a study in the journal The Cryosphere that offered what editors considered a breakthrough explanation. Their paper was selected as a highlight paper by the journal's editorial team, a recognition reserved for work considered especially significant. The team had also collaborated with scientists from NASA Goddard Space Flight Center, the University of Oxford, and ETH Zurich. Their conclusion was startling but elegant. The plumes are caused by a process called thermal convection. It is the same general process that drives the slow churning of hot rock in Earth's mantle, deep beneath our feet. The idea that ice, a solid material sitting far from any volcanic heat, could undergo thermal convection was described by Andreas Born as as wild as it is fascinating. And it turns out the physics actually supports it.
The ice sheet moves from the center to the edges like a conveyor belt and breaks off into large blocks, which go into the ocean and melt.
Thermal convection, when ice behaves like boiling pasta. Thermal convection is not a complicated idea. You have probably seen it without knowing the name. When you heat a pot of water, the water at the bottom gets hot first, becomes less dense, and rises to the top. The cooler water at the top sinks down to replace it, gets heated, and rises again. This creates a circular motion driven entirely by temperature differences. The same thing happens in Earth's mantle with semi-molten rock, just on a much slower and more powerful scale. The University of Bergen researchers found evidence that something very similar is happening deep within parts of the Greenland ice sheet. The temperature at the bottom of the ice is warmer than the temperature near the top, creating a vertical temperature difference. That difference is enough, given the right physical conditions, to drive slow circular movements inside the ice. Warm ice from the deeper layers gently rises, and cooler ice from above descends. And this churning process creates the large plume-like structures that had stumped scientists for over a decade. Robert Law, the lead author of the study, described it as an exciting freak of nature. He pointed out that while ice seems nothing like the Earth's molten mantle, the key factor is how soft ice is compared to rock. Ice is at least 1 million times softer than mantle rock, which means the same kind of temperature-driven convection can happen in ice even with far smaller temperature differences and at far lower heat levels. The physics simply works out, even if it feels counterintuitive. To reach this conclusion, the team used mathematical models originally developed to study how continents slowly drift apart over millions of years. They adapted those models for ice and tested them against real observations of the Greenland ice sheet. They also used a geodynamics modeling tool called Aspect, along with surface elevation data and detailed ice property measurements. When they checked whether the ice met 5 key conditions necessary for convection to occur, including temperature, ice thickness, density variations, snowpack, and viscosity, the results supported the thermal convection explanation.
I became very much interested in understanding how much surface meltwater is being produced, how it flows across the ice sheet's surface, and how it makes its way into the ice sheet.
Ice that is 10 times softer than scientists thought. One of the most important implications of this research is what it reveals about the physical properties of deep ice. For thermal convection to occur as observed, the ice within Greenland's interior must be significantly softer than previously assumed. Scientists now estimate that this deep ice could be up to 10 times less rigid than earlier models suggested. This finding challenges long-standing assumptions in glaciology. Traditional models treated deep ice as relatively stiff, influencing predictions about how the ice sheet flows and evolves over time. If the ice is actually much softer, it means its internal movement, deformation, and response to stress are far more dynamic than previously believed. However, researchers emphasize that softer ice does not automatically mean faster melting. Melting is primarily controlled by temperature, ocean interactions, and atmospheric conditions. As Andreas Born explained, softness mainly affects how ice moves internally, not how quickly it disappears. What this discovery truly highlights is the complexity of Greenland's ice sheet and the need for more refined models to understand its future behavior.
Scientists are calling it the most complete assessment of Greenland ice loss that's ever been captured. Dozens of separate surveys computed changes in ice mass using data from 11 different satellite missions.
Harvard hunts for the sea level fingerprint. Now here is where Harvard University steps into the story with one of the most celebrated discoveries in modern sea level science. To understand why this matters, you first need to understand something that feels completely backwards when you first hear it. When a massive ice sheet melts, sea levels near that ice sheet actually fall. This sounds wrong. The intuition is that melting ice adds water to the ocean, so nearby oceans should rise first. But that is not how it works. Massive ice sheets like Greenland's are so unimaginably heavy that they exert a genuine gravitational pull on the surrounding ocean water, drawing it toward them. When the ice melts and that gravitational pull weakens, the ocean water that was being held close to Greenland simply disperses outward. Sea levels near Greenland drop, while sea levels thousands of miles away, in places like the eastern United States or Europe, rise by more than the global average. This pattern of rise and fall, unique to each melting glacier or ice sheet, is what scientists call a sea level fingerprint. Each ice source leaves its own distinctive, traceable pattern on ocean levels around the globe. The concept has been around in theory for well over a century, and it has formed the foundation of nearly all modern sea level projections. Ocean planning, coastal infrastructure decisions, and climate adaptation models have all been built on the assumption that these fingerprints are real and follow predictable patterns. The problem was that, for all the confidence scientists had in the theory, nobody had ever actually detected a sea-level fingerprint in the real world with definitive certainty. The ocean is noisy. Tides, currents, winds, and weather all create changes in sea surface height that make it extraordinarily difficult to isolate the millimeter-scale signal from a specific melting source thousands of miles away. This was the challenge that Harvard's team set out to crack.
The urgency to address the climate crisis. This past summer saw an historic ice melt. Greenland's ice is melting much faster than it was 3 decades ago.
The satellite data that cracked the case. The story of how Harvard scientists finally detected the Greenland sea level fingerprint has all the hallmarks of great science. An unexpected data set, a quick and decisive response, and a result so clear it was almost emotional. Harvard geophysicist Jerry X. Mitrovica had spent decades working on the theoretical and computational framework for sea level fingerprints. His lab was the first to build detailed models predicting exactly what those fingerprints should look like for different melting sources. He compared the challenge of detecting fingerprints to the search for the Higgs boson particle, a subatomic particle that physicists were almost certain existed but had never directly observed. Almost everyone in the field was confident the fingerprints were real, but proving it with real-world data was another matter entirely. The breakthrough came when a European Marine Monitoring Agency released a new dataset of satellite observations. These satellites had been measuring sea surface height around Greenland, but the new data reached 10 degrees further north in latitude than previous records, pushing into the very region where the fingerprint signal would be strongest. Mitrovica and colleague David Sandwell of the Scripps Institution of Oceanography noticed the potential immediately. Mitrovica turned to Sophie Coulson, a former doctoral student from his lab, and then a postdoctoral fellow at Los Alamos National Laboratory, to run the analysis. Coulson gathered 3 decades of the best available observations on ice height change in the Greenland ice sheet, added data on glacier changes in the Canadian Arctic and Iceland, and used all of it to create a precise prediction for what the sea surface height around Greenland should look like if the fingerprint theory was correct. She then compared that prediction to the new satellite data covering 1993 to 2019. The fit was perfect, a 1-to-1 match, confirmed with more than 99.9% statistical confidence. Coulson described it as a moment of simple, remarkable clarity on complex Earth processes. The fingerprint was real, and Harvard had found it.
We're literally watching the Greenland ice sheet disappear right before our very eyes. And this is having an impact all around the planet. We all share one ocean. This is happening today, and the question is, how fast is it going to happen in the future?
Why this discovery validates nearly a century of science. The confirmation of Greenland's sea level fingerprint was far more than a single scientific milestone. It reinforced the entire framework on which modern sea level science is built. As Jerry X. Mitrovica explained, if the underlying physics had proven incorrect, decades of research would have needed to be rebuilt from the ground up. Coastal projections, flood risk assessments, and long-term planning for cities across the world all depend on this framework being accurate. What makes this finding especially powerful is the depth of data behind it. Scientists relied on more than 30 years of satellite observations, making it one of the most rigorously tested conclusions in climate science. The ability to measure the fingerprint with such precision means researchers can now move beyond theory and directly observe how different ice sources contribute to rising sea levels. This also gives scientists a new capability, working backward from ocean changes to identify their causes. By analyzing sea level patterns, researchers can now determine how much of the rise in specific regions comes from Greenland versus other sources like Antarctica. This transforms sea level science into a far more precise and evidence-driven field than it has ever been before.
After 2013, scientists actually found the rate of melting ice in Greenland had slowed down for about a year and a half, but the NASA satellites that recorded the data stopped working in 2016.
The seesaw effect and what it means for coastal cities. The concept of sea level fingerprints creates a seesaw effect that has real consequences for cities around the world. When Greenland loses ice, nearby sea levels drop, while regions far away experience higher than average increases. Conversely, melting in Antarctica shifts the balance in a way that disproportionately affects parts of the northern hemisphere. This uneven distribution of sea level rise changes how risk is calculated for major coastal areas. Jerry X. Mitrovica has emphasized that cities along the eastern United States, such as New York City, fall into zones where the fingerprint effect amplifies rising water levels. These regions are not protected by proximity to melting ice, but instead face greater exposure due to their geographic position. With the confirmation of the fingerprint through satellite data, scientists can now refine these projections with real-world evidence. The measurements match theoretical predictions closely, giving researchers confidence that current models are on the right track. Even small discrepancies, measured in millimeters, reveal the combined influence of multiple ice sources, showing just how precise modern observations have become.
In fact, if all of Greenland's ice sheet melted, sea levels could rise by 23 feet worldwide.
The hidden heat beneath Greenland's bedrock. Greenland's ice sheet rests on a foundation that is far more complex than it appears. Beneath the bedrock lies a patchwork of geothermal heat, remnants of ancient geological activity that still influence the region today. Recent studies have mapped these temperature variations in 3 dimensions, revealing that the ground beneath the ice is anything but uniform. This hidden heat plays a critical role in how the ice behaves. In areas where geothermal warmth is higher, the base of the ice can begin to melt, creating a thin layer of water that allows the glacier to slide more easily. In colder regions, the ice remains frozen to the ground, moving much more slowly and preserving the landscape beneath it. The uneven distribution of heat means that different parts of the ice sheet respond differently to environmental changes. Some areas are already primed for faster movement, while others remain stable. This complexity also ties into processes like thermal convection within the ice, showing that Greenland is not just a passive frozen mass, but an active system shaped by forces both above and below.
Others suggest the Greenland study joins a growing body of research that says estimates of climate change impacts are too conservative. All the more reason, they say, for communities and governments to accelerate their planning for ways to adapt.
Could there be more buried impact craters? The discovery of a massive crater beneath Hiawatha Glacier immediately raised an intriguing question among scientists. If such a large structure could remain hidden under ice for so long, it is entirely possible that others exist, still undiscovered. The limitations of current radar surveys mean that significant portions of Greenland's bedrock remain only partially explored. Researchers approach this possibility with caution, as evidence is still limited. While modern ice-penetrating radar has improved dramatically, it has not yet covered every region in sufficient detail to rule out additional impact structures. The existence of one hidden crater has already demonstrated that large geological features can remain completely concealed beneath thick ice. If more craters were found, especially from a similar time period, it could point to multiple impacts from a fragmented object, similar to events observed elsewhere in the solar system. For now, this remains speculative, but it highlights how much of Greenland's subsurface is still unknown and waiting to be explored.
When we put the whole picture together and we ask lake sediments and ice cores together what happened in the past, we find, I think, that the highest latitudes of Greenland change really profoundly.
How all these discoveries connect. When viewed together, recent discoveries in Greenland reveal a far more complex system than scientists once imagined. Beneath miles of ice lies an ancient tundra landscape preserved for millions of years, showing that the ice sheet has not always acted as a destructive force. In some regions, it has functioned more like a protective layer, preserving traces of Earth's distant past. Within the ice itself, processes like thermal convection demonstrate that it is not entirely static. Slow internal movement reshapes the structure over time, influenced by temperature differences and the physical properties of the ice. At the same time, geothermal heat beneath the surface adds another layer of complexity, affecting how the ice moves and melts at its base. Meanwhile, the work of Harvard University on sea level fingerprints shows how Greenland's ice sheet interacts with the global ocean in ways that are not immediately intuitive. These discoveries are not isolated findings, but interconnected pieces of a larger system, revealing a planet that is dynamic and deeply interconnected.
The ice that melted is enough to cover California in 1.25 meters of water, and that's 586 billion tons of ice.
What this changes about how we model the future. All of these findings contribute directly to one critical question: how Greenland's ice sheet will behave in the future. By studying ancient tundra preserved beneath the ice, scientists gain insight into how the ice sheet responded to past climate changes. This historical perspective helps refine long-term models and improves their accuracy. New discoveries about internal ice dynamics, including convection and softness, introduce additional factors that must be incorporated into predictive models. These insights allow scientists to better simulate how the ice sheet will flow and evolve under warming conditions. The inclusion of geothermal heat maps further improves these models by adding detail about conditions at the base of the ice. At the same time, the confirmation of sea level fingerprints allows researchers to track changes in the ocean with greater precision. By combining observational data with advanced modeling, scientists can now produce more reliable projections. This improved understanding is essential for governments and planners working to prepare for future sea level rise and its global consequences.
And we can map out and understand how much they change and how much water they deliver into the ice sheet and its impact on the ice movement towards the ocean.
The bigger picture: Earth is full of surprises. A consistent theme across all of these discoveries is how often Earth defies expectations. Greenland's ice sheet, once thought to be relatively well understood, has revealed hidden landscapes, buried impact craters, and complex internal processes that challenge earlier assumptions. Each new finding adds depth to our understanding of how the planet works. Science advances by questioning what we think we know, and Greenland continues to provide those moments of reassessment. Discoveries such as preserved tundra and internal convection are not just interesting details. They reshape the models used to understand climate and predict future change. They remind researchers that even well-studied systems can hold unexpected complexity. What makes this especially significant is that much of Greenland remains unexplored at a detailed level. As technology improves, from radar systems to satellite measurements, more of this hidden world is coming into view. These discoveries are not just academic. They are essential to understanding Earth's future and the challenges that lie ahead. Greenland holds a 3-million-year-old tundra frozen in time, enormous plumes of churning ice that nobody could explain for over a decade. A massive buried crater from an ancient cosmic impact, and it leaves a unique fingerprint on sea levels that Harvard finally confirmed with hard satellite data. Every single one of these discoveries has changed how scientists model our planet's past and future. Which of these discoveries surprised you the most? Drop your answer in the comments below.